1 over, so let's see. It looks like, let's see. Because he has something similar to this guy. All right. Yeah, that should be correct. Let's see. All right. Yo, how you doing, man?
Hey.
Yeah, I thought you weren't like I sent you something that's like I thought you went to the other link or something like that. How are you doing today?
Yeah, pretty good.
Okay. Yeah, so like I thought I wasn't gonna finish, but like I ended up well most of these are you'll see like most of these did you start your homework 6 by chance?
No, I haven't been able to. We kind of had a bit of an emergency yesterday,
Oh
so
wow. Oh man, sorry about that.
it's been a little difficult, but I mean things are okay now.
Okay. Okay. As long as you're okay. Did you at least wanna like we can go over this again maybe on like Sunday,
Okay.
but I can probably cover like most of the concepts today.
Sure.
Okay, okay. I kind of sent you some of these. I know you have like a test coming, right? So that's why I wanted to get this to you so that you can like at least study them over the weekend, or like
Yeah.
because this is like one of those critical points again. Because for the exam, I think you guys will probably touch on like solving inhomogeneous problems, and this is like the critical point because this whole entire homework is actually just that, the solving non-homogeneous equations.
Okay.
All right. So I guess to start, I'll just cover like some of these. This one, if you get a chance later on, I'll just kind of like talk about this one, and then you can review it later on. But have you heard of particular solutions? For like
Yes. The YP.
yeah, the YP guy. Yeah, YP.
I don't really know the point of it.
Okay.
Does it help
So
solve the DE?
yeah, so for the most part, you're given like a Y equation that's like whatever many this is
Mm-hmm.
equals like some type of inhomogeneous equation. So this is your non-homogeneous differential equation.
Okay.
And then like in order to solve these problems, you need to do this. So this is your general. So you can get your general or particular solution, but typically for to find like this types of equations, you need to add. It's everything that's been done before. You remember doing the homogeneous equation, the one where it's equals 0. This one equals 0.
Yes, I think so.
Okay. So when it's equal on the right hand side, this guy equals 0. That's the homogeneous equation. And then so the non-homogeneous solution, which is this guy, is only going to be a linear mapping. So you're going to have the homogeneous equation in there. So it's just going to be a linear mapping of the homogeneous equation.
So what do you mean by mapping? Is it saying one thing is the other, or?
Linear mapping means you're just adding them. That's what I mean. Like
Oh, okay.
it's like an addition of. Mapping is just like, it's like this term that they use in math where like, when you go from solution to, or differential equation to solution. So this linear mapping of homogeneous plus the particular solution. And this is where it comes out. This is where it comes up, like over here, this
Okay.
particular solution. This guy, you've seen this before, right? The homogeneous one, where you have like all of this, just to like put things into perspective. Where like when you had like, remember when for example, this guy equals like 0, right?
Mm-hmm.
And you did like k squared plus k plus 1, right? Something like that.
Mm-hmm.
And then you had like 3 solutions, 3 types of like algorithms that you can solve for the general solution. So in essence, this general solution is just this YH, right? Where you have either like, when you had like real distinct roots.
Mm-hmm.
And what was the other one? Repeated?
Repeated and so there's repeated roots, there's iterated roots or something like that.
Yep.
Oh.
Yeah, that's right. Yeah. So like the repeated and then the real distinct, and then you had complex, right? Complex
Mm-hmm.
is the third one. And then this one right here is kind of like in the form of like C1 E, right? So whatever K to the T. This K meaning this guy. K to the T. Or in this case, now let's think about this. I'm like mixing up like T's and X's. So x is going to be a yx, ek to the yx, and then this guy right here can be like c1 e to the k x, maybe like c2, and you get x right here, ek to the x, something like that, right? These are just examples. These are just examples.
Okay.
But like when you had the complex roots, you had something like this, right? Like you had like e to the k times x cosine of like x plus c2 e to the kx sine x, right? These are like examples of real distinct roots, repeated distinct roots, and complex roots, homogeneous solutions, right? Yeah.
Okay. I don't remember that they were homogeneous, but that the three types does, I do recall.
Okay. Yeah. This term homogeneous just comes into play now because there's something to like distinguish it. Like you have to categorize it from the non-homogeneous. But all of this is pretty much, y of x. And it's just a solution to when you had like whatever number of like derivatives you have for x, and then the right hand side equals 0. Or like pretty much this is the homogeneous case.
Okay. Is homogeneous the same as complementary?
Complementary,
Because
yes. Yes.
the y equals yc plus yp
Yeah. Yep.
is it's just interchangeable.
Yeah, that's a good question. So complementary or yc plus yp. Yeah.
Mm-hmm.
So this guy right here. Oh wait, hold up. Where is it? This guy right here.
Okay.
This guy right here is the same as yc of x.
Okay.
Complementary or homogeneous. Same exact thing. The complementary is the solution to the homogeneous differential equation.
Okay.
And so that's where this fits, this realm of like homogeneous versus non-homogeneous. This particular solution is what you add to this guy, the complementary or the homogeneous solution, so that you can get your non-homogeneous general solution or particular solution. It's going to become more clear once we go to the examples. But
Okay.
the reason why I'm saying this is like the particular solution is not so straightforward, but there's rules to it. Because this is like kind of like qualitative, because you have to guess this guy. You have to guess this guy. Yeah, you have to guess the guy, like, kind of like hand wavy. You guess him, and you have to perform a few things. And then it's gonna become familiar because you actually did it in homework 5. Do you remember we did the alpha and beta problem?
Okay.
Do you remember that one, the alpha beta problem, where you had to
I
like?
remember. Yeah, you'd had to calculate what alpha and beta was. I don't remember how I went about solving it.
Okay, where that problem again, like I think it was like a preview for homework 6, but that problem actually comes out in like the second problem, like of homework 6.
Mm-hmm.
So I just wanted to cover this first because a lot of the like homework 6 problems actually asks you what the particular solution is, and then I did send this to you, so like you can definitely look at it and use it as a cheat sheet. So let me just talk about it first, because the reason why you want to guess it is the reason why I'm talking about it. So when you have this part right here, the R of x, the Rx, I'm trying to how would you interpret this this table is this R of x is the right hand side of your non-homogeneous equation. So if I can erase this, let me just write something down here. So this guy, so when we have something kind of like this guy right here, like this, and now my right hand side is not 0. I'm gonna make it equal g of x, right? Or in this case, that's not how it. In this case, it's gonna be r of x. So the right hand side is gonna be r of x, which is this r of x. So this right hand side is this same thing. Like this is what this whole thing is. So depending on what your right hand side term is of your non-homogeneous equation, you have to guess your particular solution, which is this column right here.
Okay.
And then like let's go maybe look at like an example, but while we're gonna by using this table. So for example, what if your right hand side, your r of x, what if your r of x was a constant like 2, right?
Okay.
So this is that first guy right here, the first row.
Yeah.
So if r of x equals 2, and then the problem is asking you what is the particular solution. So you look at this side, the column, and so you look at this guy, yp of x for r of x equals 2, where 2 is obviously a constant. You just look at this. What does it say? It says that a equals a constant, right? Or big A, where a equals a constant. A meaning this guy right here.
Okay.
Or like this is a constant. That's what a is a constant. That's what it's saying. So you just write this. All you have to do, this particular solution, is just a. And a, you're gonna have to solve for a, like afterwards. But right now, just take it as like, okay, you have a right hand side. You have a right hand side that's a constant. It could be a 2, it could be 1, whatever, constant, no variable.
Mm-hmm.
And then your particular solution, initial guess, is just a, an arbitrary constant. Does that one make sense?
Yes.
Okay. So what if it's not that? Let's take a look at another one. So what if your right hand side is this guy now? This, maybe let's say like 3x plus 4.
Okay.
And then the
That
question
would
is
be
what?
linear.
Yeah. What is your yp now?
That would be ax plus b.
Exactly, ax plus b. Okay, this one's an easy one, but let me actually like put a twist on this. So what if they only ask you, what if they only gave you r of x, the right hand side is 3x? What is your yp of x?
It would still be ax plus b with b as 0.
Yeah, but you carry it out though. Yeah, that's correct. You carry it out. It's the same thing, ax plus b. You always, like every time it gives you this power, or this polynomial power, you always still need to put in the lower powers of the polynomial. But once we start solving for these coefficients, because if you just make them 0 right now, you won't be able to solve for it, right?
Mm-hmm. So you couldn't just put 3x plus 0 in there?
You could put 3x plus 0, and this is a constant. 0 is a constant, right?
Uh-huh.
But like what I mean is like once you put this, once you have this ax plus b as your particular solution, you don't want to like directly say that b equals 0. You don't want to directly say b equals 0.
Mm-hmm.
And then drop it, because then it's gonna mess around with your equation, and you won't be able to solve for the right a. If you drop b, you won't be able to solve for the right a. So even though, yes, in the real right hand side, b is 0, you still should carry out the b as if it's not 0, and see, after, because like after you do this, right, after you have this particular solution,
Yeah.
you're gonna put this in the full solution, right?
Mm-hmm.
Which is like,
yeah, I mean, that's what I was planning on doing. I was just saying like b is 0 to keep in mind, but still write ax plus b as your yp. In
the end, I think b is 0 for the most part. I mean, for me, like what I usually do is like I don't like trying to create trying to follow shortcuts, because for the most part I've seen it like mess around with you solving for a, and you won't have the same amount of coefficients. What I'm saying, like you don't have enough equations. You won't have enough equations to solve for your for your coefficients, and then you're gonna be like, what? Where's my other equation? Like, where's my other equation? So if you make this 0, you're gonna be losing one equation. But if you carry it out, you're gonna have exactly the same amount of equation as the same amount of coefficients, which shouldn't be an issue once you have that. But that's gonna make sense once you do more of the problems.
Okay.
Like, oh, that's why I don't want to make that 0. But anyways, like, once you have that, the reason why is you're gonna solve for the coefficients here once you put it back in the the main equation. Okay. So does it make sense how to read the table now?
Yeah.
Okay. There's obviously more that you can do with this table, but we'll just attack the problem one by one, just to like and then use this table as like a guidebook.
Yeah. So will you ever have to manipulate what you're given as Rx in order to try to see if it can match one of these forms?
Yeah, like number 1. You talking about number 1?
Well, I didn't look at number 1. I was just like asking in general because I know there are other things I've done, I think, in calculus where you had to match your equation or whatever to one of the forms given.
Oh yeah, I think I know.
And I don't remember what kind of topic that was, but I just remember distinctly doing something like that.
Yeah, it's kind of like that. For the most part, this table is pretty comprehensive. It's general, but it does cover a lot of ground. The one thing it probably doesn't cover is like when something is being divided.
Mm-hmm.
Like this guy. Like what if you're dividing this guy? Like this one right here.
Yeah.
This is the part where you always have to match the form. The E, when you have an E,
Mm-hmm.
like you always have to match the form where you have to account for it. Where you have like, okay, you have like A here, right? And then you have like this T, and then E to the negative T. You have to match the form, right?
Yeah.
And then you look at this guy. This is a polynomial, right?
Mm-hmm.
So you would divide this by the full power, for all the lower powers as well. So you have like BT squared plus CT plus D. This is kind of similar to like what if you had what if your right hand side was let's see, like 2 minus this guy plus maybe like T squared plus 1, or actually maybe something harder. Let me see if there was one that's harder here. Oh, okay. Like cosine of T. Let's make this harder. Cosine of 2T. So what if you had that one? Then you still have to match this. So this would be like A E minus T cosine of 2. This is the only one that lingers. This one becomes a coefficient.
Mm-hmm.
But then you need the other one, right? You need the sine counterpart. But then it has to be kind of like a similar it's kind of like a similar form.
Okay. Would you just multiply that by 2?
For which one?
For just the whole thing, because it's the e to the negative t cosine of 2t. That whole thing is what you already written. The a of e to the negative t cosine 2t plus b e to the negative t sine 2t. But you still have that 2 in front. So would you multiply that whole thing by 2, or
okay?
by the first part, or
so if your coefficient or if your constant is like inside one of these guys, or inside this guy,
mm-hmm.
it carries through. You have to put it the same form. But if your constant or coefficient is in front, like this,
yeah,
it doesn't carry over. It's gonna be a coefficient, an arbitrary coefficient.
Oh, so a, I know you don't directly substitute, but the idea is that a and b would both be 2.
A and B does not have to be 2. Like you have to solve for them.
Okay, I was just trying to think of like how to identify the form. like
So
in your mind you would think kind of for that one, at that one point you would think 2 would be A and B, and then you would just
it
kind
seems
of
that way,
ignore
yeah.
it.
So like I usually what I would do is I would never account for like making this 2. Like if it's like a base like being multiplied by itself, not inside any of these like transcendental functions. Like if the coefficient is inside these transcendental or like trigonometric functions, you carry them over. You always carry them over, but you should never carry over a 2 here. Like
That coefficient in the front.
yeah, you should never carry that over.
Okay, so how do you then identify what that is if you can't do that?
Like how do you? Well, the main thing, like the procedure is, so now you have this guy, right?
Well, I mean, like, without knowing that, like when you're doing the initial analysis and trying to refer to the chart, how do you know that that form is what that is without doing any assumptions?
Okay, so take a look at this guy. Or where is it? Here you go. If you look at this chart, where's this guy? I think it's right here. This one right here.
Okay.
So a lot of these there's obviously constants because they're making it arbitrary. So you see this small a and small b, small a, small b.
Right.
So small a, small b can be any arbitrary constant, any arbitrary constant. Let's take a look at what its forms is supposed to be for the particular solution. So this is the particular solution, right?
Uh-huh.
Did the small a, small b carry over?
No.
No, yeah. So you leave those out, but there's things that carried over, right?
Yeah. The betas.
The betas and alphas, yeah.
Yeah, and I completely understand that, but like I know that there are things that don't carry over, but like
okay.
I guess I'm just confused on why you can't make assumptions like what doesn't carry over, being
I
your
understand. Like, okay,
lowercase a's and b's.
it's just the form of it. Like you just
Yeah.
you just have to follow. That's why it's a little bit hand wavy. Like it's like but there is this is the table that people usually use instead of like guessing out of their mind. At least there's like a form that you can follow, like a system.
Okay.
Yeah. The letters, the small letters, if you can like convince yourself
Yeah.
that the small letters are not, not the alpha, not the Greek letter beta, but
Right.
the small letters. Same with this guy, the small letters, right? The A and B.
Uh-huh.
It doesn't carry over.
Right. And
yeah,
I know that it's like, but what would the small letters be in this case?
it could
The
be
A's
anything. It
the
can be
A's
anything.
and B's. So what in our given problem, that what would be considered like the small A's and B's?
Our given problem, this is the cosine one, right? This is the one with the cosine.
Mm-hmm.
So let's look at that problem. Let's look at this like left hand, left column. So there's a cosine right there, right?
Right.
And then the cosine has the a, the small a, not the alpha, as the coefficient, right?
Right.
So our 2 is the a.
Okay. Yeah.
And then b is the 0.
So that's the B's a 0.
Yeah. But
okay.
Yeah, this is totally like what it is. Like the a's and the b's, the small a's, for all of these, this is how you read it. There's even one where, when there's more than one of those guys,
Mm-hmm.
you can really like pick those out. But
Okay.
And that's why if you look at like that homework problem, there's a big A2 and big A1 and big A0. Do you remember looking at that?
Mm-hmm.
From homework 5, I think number 6 or something like that. Okay.
Let's see. I can't
Whichever
remember
one.
which one.
I know it's like homework 5, one of the later questions.
Yeah. Okay. That answers my question, because I was like wondering, because I completely know that you don't carry over the 2, but in order to identify the form, I was just wondering, how do you know that that's the form? Because I mean, you would have to make the assumption that A is 2 here and B is 0.
Yep.
But I know completely that you don't carry over that 2 anywhere in our form. I was just really wondering
what the small a was. Okay.
Yeah, what the small a was. And because I mean, like the twos there, you have, whenever you're finding the form in the table, you have to account for everything there. Maybe you don't carry stuff over, but okay, I
Yeah,
was just,
it makes
okay.
sense. It's a valid question. It makes sense. Like a lot of these constants, they'll never, for the most part, like you'll never really work with numbers. Like you have to get used to like just making your assumptions. Like they give you something general, and it's
Yeah.
up to you. Given what you have here, it's up to you to give some life to it, or like assume that small a is that,
Mm-hmm.
given a real equation. Yeah. So that, in essence, yeah. Does it make sense how to read this table?
Yeah.
Okay. It does get complicated, but let's just look at this guy, and this is number one. Number one asks you. It doesn't tell you to solve it yet. It just tells you what is the particular solution, knowing the right hand side. So let's take a look at that. This one, as I said, I think I was really referring back to this while I was doing the the e to the t problem over something. This is how I would do it. So the 13 is just pretty much, that's one of your a's. That's pretty much the a. So, and then you substitute a big A for that, for the particular solution. And then you keep everything that's inside a transcendental or exponential.
Okay. What is a transcendental function versus an exponential? Because I've looked at different calculus textbooks. Some of them say transcendental, and then some of them say non-transcendental function. So what exactly is the definition of both?
It's a good question. For the most part, I just always associate them with like non-polynomials. That's that's not a polynomial. That's pretty much what it is.
Okay, so a transcendental is basically more than just the simple polynomial.
Yeah, well, because you have numerics, right? You have numerical numbers. You have polynomials, and then what about everything else? What about cosines? What are these guys? Another
Yeah.
name for these ones: sines, cosines. They're trigonometric, obviously.
Trigonometric. Mm-hmm.
And then there's these guys, which are exponential. But then this group of guys, they just called transcendental.
Okay.
Non-polynomials. Okay, non-numerics. Okay, so in essence, yeah, anything that's inside the transcendental, that means you carry it over. So, and then what about this guy? You just do the same thing, right? But he has to be part of the E. You never separate it. He has to be part of the E. So it takes the same form. But then since it's a polynomial, the rule is even if it's not showing all the powers of it, power terms, you still include all the power terms, the lower power terms. So that's the answer for this guy.
Okay.
And then it's not fun. The number one wasn't fun because it doesn't you don't really see the full story of like how you solve these or inhomogeneous equations.
Yeah. So really all we're doing here is we're just converting we're just identifying what our kind of like our forms are, and then just using that as our answer.
Kind of. For this one, or like, are you talking about this guy?
Well, I'm not talking about like the whole process. I'm just talking about in the first problem where they're just asking for a particular solution. You would basically have that a to the a times e to the negative 3t over bt squared plus ct plus d, and that would be our answer.
Yeah, actually, let me go back. Let me see. Let me go back. It's actually, the answer here is I'm looking at this now again. It's minus t. It's minus t because you have to keep the form here. Yeah. Now go back to your question. Yeah, that's all you have to do. You pick it up from that table.
Okay. So let me see here. So divided by bt squared plus c t.
The one thing about this is like, I don't know how they're gonna assess this A's, B's, and C's and D's. I don't know how they're gonna assess this one.
Yeah, I mean, there's unlimited attempts, so that's the good part.
Because like the other ones, they tell you the C1 is like C sub 1 is like C and 1, right? They tell you to type C1. But I don't know about these ones because they don't tell you. I don't know.
Yeah, there's no A, B, C's, or D's here. So I guess you're going to have to just do the finder C1, value C2, that kind of thing, put in that form, I guess, or
Okay,
I don't know.
yeah.
Because I tried putting in the A, E to negative T, but it didn't. It just said a variable A is not defined in this context.
See, this is why I don't like that. Like, you should ask your professor maybe. I don't know if they programmed it. Like, what are you supposed to put in there?
He doesn't even know how they
He doesn't even
program
know.
it. Yeah, because it's not. He doesn't create this like the problems themselves, the solutions. He just uses the database that they provide. So
I see what you're saying. That's really no hope there.
So then
maybe there's a contact, because like they don't tell you what to put, and then there's no way. And the thing is, this is only asking for that, right? It's not asking for the full solution.
Mm-hmm.
It's not asking for the full solution. I don't know.
Maybe it's just T. Maybe it's just the right side. Maybe. Let me see.
Let me think.
No, that's not it. Okay.
Let's try the other ones, because like if you take a look at there's actually a problem that looks similar to this, like number 6. Look at number 6.
6. Wow. Okay.
So these ones, like, it already gives you the answer, right?
Mm-hmm.
And then you just have to match them. So let's see. Seems like you have to use A though, right? I mean, these are the solutions.
Yeah. I mean, these aren't too difficult.
Yeah.
Because you just have to match. Because I don't know why. Unless you have to use a different style of lettering for this, like a backslash math and then A.
You mean the latex?
Yeah, the latex notation.
Crazy. Of it. That's like, you should definitely like contact whoever made that software. It's so frustrating. I know what you're talking about. Like if you're putting that, I know you have a limited, but at times, but they should still be like descriptive in how you're gonna place that. I don't know. Okay, can we move on though? Because this one is the answer is this. I'm pretty sure.
Yeah.
Okay. So for number 2, do you remember this? This is kind of similar.
Okay. Find alpha and beta. Okay, so let me see.
And then
so you do a general solution.
Okay, yeah. I want you to tell me how you would do this one, because we've already done this one actually, but this is just different numbers, different like right hand side, and different YP.
Mm-hmm.
But this guy is the same. When I say the same, it's like the same as I think homework 5.
Okay. All right. So let's see. So we have a differential equation: y double prime plus alpha y prime plus beta y equals t plus e to the 4t.
Yep.
Okay. So then we have the particular solution given.
Yep.
So then determine alpha and beta. So I mean, they don't really give a lot of numerical answers here.
Yeah, that's why it's like, but then looking at this, this is just something to like an aside, but I feel like it's important. Now that we talked about the whole particular solution, because in homework 5, you never went over that one. And then like now that you see like, oh, there's a YP here with A1, A0, and B0, it makes sense why they have this now, right? Looking at this guy.
Not really. So
it's like omitting a few other terms, but they're leaving it up to you to like place those 0 terms. There's some 0 terms that they're omitting. Because like how this power isn't up to the 1, right? It's like t squared t, and then where's the other guy?
Yeah, there's a.
And why is there a t squared?
T and but there's no constant one.
Yeah, and why is there a t squared? This is only 1, right?
Well, I mean, there's a double prime, a y double prime.
Yeah, but then like when you're looking at the particular solution, you're supposed to only base it off the right hand side.
Oh.
But like that's besides the point. What I'm trying to say is some problems they'll give you the particular solution and then you just have to go with it. And then other problems you have to make an assumption, and that's when you apply that. But don't try to like read into this problem too much and say like, oh, why are they doing t squared? You know.
So would alpha be just like A1?
No. So do you remember how we did it?
So if I recall, you have to create a general solution.
Yeah, but then like for me, like just so that we have like a procedure, I think because I think you're gonna see this problem again. I can guarantee you, like maybe 99% that you're probably gonna see this problem again because this is the second time it shows up. It showed up.
Yeah.
So like I guess just memorize and then like know, or it's better if you know like why. But the very first thing is, you know, you have this yp, right?
Uh-huh.
And this yp, just take its derivatives, first and second. So yeah, so then you know, and then I'll tell you why after. So like,
well, it's a second order, so you would do two derivatives.
You do two derivatives, yeah, first and second, and then you have the yp. So that's what you have. You just take the derivative, and then the next thing here, then there's no harm in doing that. The next thing is like a little bit weird, but then now you find alpha and beta. But how do you do that? You do that. You have this yp, right? Yp derivatives.
Mm-hmm.
You have this yp derivatives, and then so what you need to do is you're gonna have to assume, or I guess I'll just say this: you're gonna have to assume that yp is a solution to the differential equation, which it is. It's a particular solution. So what you have to do is use that differential equation, and wherever you see the y, wherever you see the y, put the particular solution there.
I don't know. So
that's what you have to do, though. Like the reason why you could do that is because it's a solution to the differential equation.
So you would replace y with yp?
Yeah, this trick, this whatever we're doing right now, this is there's a particular name for this. It's called the method, and this is one of those like, okay, you have to remember this because the first, I think, what was it? The first differential equation, the first order differential equation. You had that whole what was that called? Do you remember what it's called? The undetermined coefficient. I think that's what it's called.
I don't remember.
The way when you solve for the first order differential equation, there's a method, right? The method is called, and then like there's obviously going to be part of the first exam or like the exam. When you solve it, when you're solving for these guys, let me look. Oh yeah, the integrating factor. The integrating factor. Do you remember that one?
Okay, yeah, that was the integral of the y t dt or something.
Yeah. So that one, like, that's a critical point as well. Like, you need to remember how to do that algorithm, the integrating factor. How do you go about in solving a first order differential equation? And then you guys went to second order. So second order, there's the homogeneous part where the right hand side is 0. And then I talked about it, the 3 different solution algorithms, right? Depending on the characteristic equation, the solution, you have 3 different ways that your general solution can work. But then now another critical point is solving an inhomogeneous second order differential equation. And this method is called a method of undetermined coefficients. So this is another name, another rule. It's the same as the one where you have variable coefficients for second order, and then it's like a homogeneous, so that's variable coefficients, not constant coefficients. This one is you have an inhomogeneous equation, and then the method is called method of undetermined coefficients. And then that's just a long ways of saying this is what we have to do. You have a particular solution, and then you make the particular solution a solution to the differential equation by doing this, by substituting the yp, the particular solution, to the differential equation. This is this method. The reason why we can do that is because this method says that you could do it.
I don't know. So could you kind of explain that last part just a little bit more? I kind of got a little lost.
Okay, which part? Which part?
Okay, so the method of undetermined coefficients. So could you kind of explain that again and how that relates here?
Okay. So method of undetermined coefficient is just a name, it's just a name of a particular algorithm. With all these differential equations, there's always someone who created an algorithm. An algorithm is just a way to solve a solution. So someone name it method of undetermined coefficients. And when you look at this guy, this is a inhomogeneous equation, right? This guy right here.
Okay.
It's
the top of the line or the bottom?
Top of the line.
Top of the line. Okay, so the whole y double prime plus alpha y prime plus y. Okay.
So this guy, the reason why it's inhomogeneous and second order because this guy is second order. Why it's non-homogeneous is because
it's not equal to 0.
The right-hand side is not equal to 0.
Mm-hmm.
When you see that, it's always just, can I fit like an algorithm to an equation? It's always just, which algorithm do I use for this situation? When you see something like this, your mind should go method of undetermined coefficients. And what is first let me say why it is called an undetermined coefficient. Is because you have this A1 B naught, you've seen this, right, from the equation, from the table.
A1 B naught.
Yeah, this YP, the particular solution, you have these bunch of coefficients, right, that pop out. You have like A's, B's, A1, B naught, or whatever coefficient you're going to use. This particular solution has undetermined coefficients, right? They're undetermined right now.
Undetermined coefficients.
Yeah, they're undetermined right now, but you
wouldn't that be 2 and 8 and 16?
No, those are constants. The coefficients,
because coefficients are in front of your variable,
but these are assume. Yeah, you're right. Yeah, I know, and that is in fact correct. When you're saying like this is any variable that's in front, any coefficient in front of variable is a coefficient, right? This is a variable. A1 can be a variable, right? Obviously. Mm-hmm. But in this case, when they're saying undetermined coefficients, it's undetermined, right? This one's obviously determined. It has to be these guys because you are going to determine them. And you cannot call them like, if you remember, there's constant and variable coefficients. That's only for homogeneous cases. When you have an inhomogeneous case, I mean, yeah, you could call it C1, C2, right? You can call it C1, C2.
Yeah.
What have you? And the C1, C2, usually the C1s and C2, you've seen this before. These only show up in the complementary solution, right?
Okay, let's see. So C1, C2, C3 only in complementary.
Yeah, but if you look at the particular solution, you could use C1, C2. But for me and for everyone else, they usually write these A1s, B1s, B2s, and then B naughts. That's what they use, so that so you don't get confused that they're not part of the complementary solution.
Okay. Also, if that's the case, couldn't this still be C1, C2, and C3? Because if it's only in complementary, because the other one is homogeneous plus complementary, gives you your, I guess your answer, total. Your total. Yeah. And since this is a non-homogeneous, it could be because since it, if C1, C2, and C3 are only in YC. Not in the homogeneous, and if this isn't a homogeneous equation, wouldn't that still be valid?
Say that again. There's like a lot of stuff.
Yeah, I know. So there's two parts to the solution. It's either complementary or homogeneous.
Yeah.
Since this equation is non-homogeneous, shouldn't it be complementary? And if that's the case, couldn't A1 B naught be the C1s and the C2s?
Yeah. Okay. I think I understand. So The C1, C2, C3, A1, B naught, B, it's all up to you. Like, what are these guys? C1, C2, what are these guys? A1, B naught. Are they coefficients? They're constant coefficients, right? They're constant coefficients, right? Or I think that's
The
what
twos and the eights, those are constant coefficients.
it's just a constant in this. When they say coefficient, usually in math, like when they say coefficient, like what is coefficient? Like that's just, it's not. You have to
Well,
say it's constant. It doesn't have to be constant.
the prefix co means with.
Yeah, but in math, what is a coefficient? Like in terms of like math.
I don't know. I'll have to look up the definition because I guess I was just told. So it's a numerical constant quantity placed before and multiplying the variable in algebraic expression.
Yeah, what you know, that thing in here in front of the variable right here, this guy,
Mm-hmm.
which is kind of like this guy, right?
Yeah.
Okay, so in technicality, like to be, you know, when someone says a coefficient, I mean, yes, these are coefficients, and then the A1 can be a variable, but then that that's just like, you know, up to the person trying to like think about it, like in terms of, oh yeah, of course it's a coefficient, but then the guy who created this undetermined coefficient, what he was referring to were these coefficients that you have to solve for, or the letters, the variables that you have to solve for. That's what he meant by them. That when it's undetermined, because you have to determine what these guys are. I guess
So
okay.
2 and A1 are both coefficients. It's just the determined coefficient is the 2.
2. Yes. Yeah. I mean, you can think about it that way. Same with the 8 and 16. Yeah. You don't have to determine them, but then you still have something to determine, which are these A1s, right, and B naughts. But I think going back to the question, if you had like C1, C2, C3 in your complementary, and then you had like A1s, B naughts in your particular, you could still use and continue this numbering. Like if you use C1, C2, C3 in your complementary, you could just use like C4 here and then C5.
Mm-hmm.
It's completely up to you.
So YP is
Because
2A1 plus 8B
because in the end,
not E14 plus 16B not TE40.
yeah. Because in the end, you're not gonna. It doesn't matter what you call the C1, C2, what in the end. What matters is you solve for them, and then it's just the number, right? It's just the number that matters, right? In the end. The one thing is though, the one thing is we still don't know how to input number 1, right?
C5 is B naught. Okay. I'm sorry. Could you repeat that? So.
Okay.
Y. So Y double prime. We don't know what our answer is. Are you saying?
So Y double prime and then Y prime, even Y prime has these guys. These are just going to be coefficients, you know, A1, A naught, B naught, that you have to determine. You don't know what they are now, but you will, is what I'm saying. You don't know what they are fully. You know their equation, but now the next step is figuring out what. For now, you don't have to figure out what these guys are. In number 4 and 5, or number 5, in number 5, problem 5, you have to determine what these guys are.
Okay. I'm wondering. So on here, I'm trying to understand how you got from the first to the second derivative.
Okay.
I understand that, like, since you're doing, these are pretty simple because you just bring down the what's being multiplied like on the top by t and bring that down in front. But I understand that it's the third part, the 4b naught te, or the 4t. You would bring down the 4, so you would have 16 b naught te to the 4t. But for the first b naught,
First B naught.
wouldn't it just be 4b naught e to the 4t? How is it 8?
Oh, it's 8 because this term right here, this guy, right? Let's go over the derivative. So this guy, what's the derivative of this guy?
Which one?
Here, I'll change colors. What's the derivative of this guy?
Oh, that would be 4b naught e to the 4t.
This guy, right? This guy. That's what I have right here. Because then, like, this guy is the derivative of it is 4b naught e to the 4t.
Right.
Okay, so what about this guy? What do you have to do with this guy?
Well, that would be 16 b naught t to the t e to the 4t.
But then you have a t here. You have a t there. Don't you have to do something? You have to do a product rule, right?
Okay.
And that's why you get two terms. That's how you get two terms.
Okay, how would you product rule here? What would be your f and your g?
So your f here, well, so 4b naught is pretty much a constant. It's a coefficient. 4b naught is a constant coefficient in this case. And then so it doesn't matter.
So you're just differentiating with respect to t?
Yes, this whole thing is respect to t, yeah. So your f here would be t, and then your g here would be e to the 4t. Right? Your f would be t, and g is e to the 4t.
Yeah.
And that's it. So yeah, you can do that. You can do that one.
Okay, so I need to have some time to like expand that first. So
Okay.
product rule. Your f is 4b naught.
Yeah.
G is t e to the 4t.
This
F.
one, like when it could get more complicated, especially with differential equations. Those rules will carry over, from calculus 1 and 2.
So then f prime would be 4, and g prime would just be 4t e to the 4t.
Yeah.
So
And you times the 4b naught in there.
4b naught times 4t e to the 4t plus t e to the 4t times 4.
Yeah.
That's going to be 16 b naught t e to the 4t plus 4t e to the 4t. Okay.
So the t part is like 1, so that's the 4b naught e to the 4t. The t is like 1, and then so that's why you get this term right here. That's how you get like this 4b naught and this 4b naught. So they become 8, right? You could add them.
Okay.
Okay. Does that one make sense? This yp now? Y the over p? Okay. Okay, so no, that's the very first step. The very first step is calculate your yp derivatives. And then just for this problem though, because I think this is going to show up, after you do that, you find alpha and beta, and you do that by the method of undetermined coefficients. That's just you plug in the yp derivatives in the differential equation, and then the next thing, we did this in homework 5, is you solve, after you plug them in, right? After you plug them in, you simplify, or in essence, simplify means like expand them, like distribute the alpha, distribute the beta, right? Distribute the alpha, distribute the beta, because that's in this equation right here. And then this is where it gets complicated, but the more you do this, the better you get at it. The more you do this is, like, after you do that, what you have to do, so this is the equal sign, this is pretty much like expanded, is after you distribute the alpha and the beta, you're going to get all these terms in terms of like 1, in terms of e to the 4t, in terms of t to the times e to the 4t, times 1, e to the 4t terms, t to the e to the 4t, and then you have like t squared terms. You have a t, and then t to the e to the 4t. You're going to get that all on the left-hand side because you distributed the alpha. And then on the right-hand side, what was our right-hand side? We had t plus e to the 4t, right? On the right-hand side?
Yeah, it's on the right.
It's crap. Doing that. Okay, yeah. This guy, right? This guy. So, does it make sense what I did here?
No. It's the very first part where you're like, I don't understand how you distribute the alpha beta. Like, what did you plug in for there? So
You just
What
distribute
after
them.
you do the after you take the derivatives, what is your answer? Is it that 2a1 plus 8b not e to the 4t plus 16b not t e to the 4t?
What is what answer? We didn't find the answer yet.
No, after you take the second derivative.
The second derivative. You want to know what the second derivative is?
No, like I don't know how you added together the alpha and the beta. What did you add it from? What was the original before you distributed the alpha and beta?
What was the original? It's this guy. It's these guys.
Okay,
Everything
how
in
did
here.
you get that?
You just plug in what you know in the
With
differential equation.
into what?
The differential equation. What was the differential equation? Right? What was the differential equation?
2a1.
Right? What's the differential equation? It's this guy, right?
Double prime, okay.
This is just the method. The method algorithm is to do this. After you get the particular solution, you plug them in back to the differential equation.
Double prime.
Okay, I think we need to do more of these ones. It's gonna make more sense if we go to 5, but if you are gonna see this problem, you have to do the same thing.
Okay, where did you get the y double prime p plus alpha y prime p plus beta y p from?
This is the differential equation, right? It's given to you.
Yeah, is that y? I know you. I think you swapped it for something.
The y in there in the differential equation, you have to. It's a solution, the particular solution. You have to swap it for the y. Wherever you see the y in the differential equation, you have to swap it.
Okay, wait, but the y double prime p. I know you. What do you mean by you have to swap it?
What I mean is like every time when you see the y in the differential equation, you put in the yp. That's what I mean. So if y prime, y double prime, and you put in yp double prime. When you see y1 prime, you put yp1 prime. And when you see just y, like beta y, you put in beta times yp.
Okay, so you replace y with yp, and then after you replace y with yp, what do you do next?
The next thing there is you just substitute what you did in the previous, which is you got the y, you're given the yp, so that's good. Now you substitute in y1 prime p and then y double prime p.
Okay, so you input your derivatives. Then what do you do with alpha and beta?
You distribute them, you times them, right? You times it to y, well, alpha you times to y1 prime, and beta you times to y0 prime. So beta times yp, alpha times y prime p. In this case, it could be something different if it gives you something different.
Okay. Then from there you do distribute it out.
Yep.
Okay.
And then
Beta. Is there a difference between a beta and just beta not?
yeah, there's a bit. It's the Greek thing. It's a Greek letter. You can't combine those. It's gonna make it mess it up. You have to keep those separate.
Yeah, because I know sometimes you on some of the parts you have alpha or you have A1 beta and then A1 beta naught on some of these?
Yeah, once you distribute them, they're gonna times, right? Now, once you distribute them, they're gonna multiply. You know, you're gonna distribute this guy to this guy.
I know we have beta, but where did we get beta naught from? Where did that come in?
That was part of the solution, the YP. They give that to you. They give it to you right here. And if you look at the problem, they have it as B naught, right?
Yeah, so it becomes beta naught?
No, it's just B naught.
Wait.
It's just B
Okay.
naught. It's
So,
not beta.
Okay. So it's, so it's not a beta, that's a B.
Yep. Yeah. Well, if you, yeah, obviously my writing sucks, but like, yeah, once you do it, you know, you write it down yourself. You're gonna see, yeah, you have to keep them separate.
Okay, why did all the alphas, I mean the A's and the B's disappear?
Where?
So where you circled the equal sign in green,
Yeah.
before, yeah, like from there, I don't see any.
Before the equal sign.
Well, like after the equal sign, there's no, in your answer there for like those two lines, those two rows, there's
Okay.
no A's or B's anywhere.
There isn't, yeah, because this guy is only, there's no A or B in here, right? It's like it's only T's and T. There's only T's. So you have like this guy. This is probably like a harder part to like take in, but you have this one T here, right? And you have one E4T, right? You have one T and one E4T, right? On your right hand side.
Okay,
Right?
there's a T and an E4T. Okay.
Okay, so let's take a look at where are those guys. So those guys are right here. One T and then one E4T. Is there something weird? Is there something weird about this side? So I have only two terms, and now I have like these other guys, right?
Okay, so above the equals, are you saying that's the right side, or like the equals and then the two lines after the equal sign, is that the right side, or did you convert the left side into a new form?
Okay.
Like, how, I'm just kind of don't know how to know whether when you write equals, if you mean you're still looking at the original equation, but with, things plugged in.
Yeah.
And so it separates the left from the right side, or whether you were just working on one part and then turned it into the next, like to the next form. Or
it's really up to you. Like the thing is, I'm gonna write it the way I write it. Like I'm gonna write like it. I don't want to write it in a way that's like super clean, because like it takes so much time to like clean it up. But it's up to you how you're gonna write it. But what I can say is this part right here is the left hand side, right? And then this right here is the right hand side.
Okay.
And obviously when I say left hand side, that's left hand side of the equation, the equal sign. And when I say right hand side, that means like that right hand side of the equal sign. Yeah, you have to write these down, like, actually like solve them like step by step, because the moment when you look at it, right now, it doesn't make sense. But the moment when you finally write it down yourself, it's like, oh shoot, because like it's the steps that really matter. The steps of like performing the math, like why you have to put things in like especially this next part is really, it's not difficult, but why are you doing it? It's more like this method of undetermined coefficients, this is what you have to do.
Okay, so you just compare each, I guess, T squared and the E to the 4T's together.
But do you know how I got these? So you know how like we have T here, right? And then E to the 4T. So this is the 1T and E to the 4T, but for the undetermined coefficients, you have to expand them. You have to expand the right-hand side. You have to expand it so that you have, even if you didn't have a T squared, you times it by 0. Even if you didn't have like a 1, you times it by 0.
Mm-hmm.
And then even if you didn't have like a t to the 4t, you times it by 0. So you have 5 terms instead of like 2.
5 terms instead of 2.
Yeah, because you have t plus e to the 4t, that's 2 terms. But then obviously the reason why you do this is because it's you have to solve for the, in number 5 you'll see it, you have to solve for the a naughts, a1, you know, all these a's. But this one it doesn't matter because we're only solving for the alpha and beta.
I still don't understand why you turn 2 into 5. So is it because you account for the additional terms that aren't included on both sides?
Yes, yeah, that's exactly it. That's exactly it, yeah. Because 2 terms become 5, but then there's 0 in, because they're not in the real, you know, they're not here. This is what we have, but they're not in there. But in math, you could do that so that you could solve for the coefficients. And that's what you have to do. You have to solve for the undetermined coefficients.
Okay, which terms did you, so I know there's a t and a e to the 4t on both sides, but which things do you have to account for?
Which terms?
Like which other terms do you have to account for?
Okay. So, you know, do you remember, let me think. Let's look at this one. Which is better to say. Okay. So, do you remember he gives you the yp, right? The yp is given, right?
Okay.
And then so the yp, you take a look at this guy. And you already know, I mean, this yp has a t-squared term, right?
Yp has a t-squared term.
Yeah. And it also has a t term, which is okay. It's already in the right-hand side.
Mm-hmm.
And then, like, what did we say? What we need to account for if we have like a t squared and a t? We need to complete the polynomial, right? We need to give all the, you know, you have the 0 power polynomial, you have the 1 power polynomial, and then you have the 1, right? This 1 is t to the 0, right?
Uh-huh.
Okay. And then what else do we need to account for? So we have t squared terms, we have t1 terms, we have t0 terms. The other thing is what? T to the,
yeah, t to the 4t. So do you need to make any additional like simplifications? Like, you know, you have a t squared can be simplified into the t to the first and t to the 0. So do you have to turn the t e to the 4t to lower terms? Also, if you don't, but in cases you do, like how would you further simplify the t e to the 4t?
How do you simplify the t e, this guy?
Yeah,
You don't really simplify. It's more like what's more straightforward is when you see a polynomial, you include all the terms.
Yeah, like if you, let's say, like for example, something simple is like t to the 5th versus, and then the lowest power term that you have to account for is, let's say, just a number. I know that everything in between is t to the 4th, t to the 3rd, t squared, t, and then, yeah. Yep. But let's say you had t e to the 4t and there is a lower power term, which ones would go in between? So
okay, so for example, that's like a lot too. So did you say t to the what?
so let's say you have just like that form, t e to the 4t,
Okay.
in the similar way as you did before with the t squared, you know, becoming 1, which is the most simple.
Yeah.
How would you
Okay.
simplify t e to the 4t, like in
Not
order?
really simplify, but like account for all the terms. Account for the
Yeah,
terms.
I guess, yeah, the
Okay.
math way of saying it.
Yeah, you have to be precise. No, I'm just kidding. The t e to the 4t is kind of similar. The e to the 4t doesn't matter. You don't simplify that, right?
Mm-hmm.
Like, or account for the terms. So since this is to the 1, you also have to account for t to the 0, right?
Yeah,
Times
so
e
it'd
to the
just be
4t.
e to the 4t. You wouldn't do any further simplifications with the e to the 4t. You wouldn't have like a 3t, 2t, t, and then 0.
Don't do that one. Yeah,
Okay.
that's, you should never do that. Yeah, never
So
do that.
basically, non-transcendental things you would.
Yes. Yep. You're getting it now. Yeah.
Okay.
Non-transcendental things always stay the same. cosine, sine. You never account for lower power. Good.
Okay.
It's not really lower power, but then for the polynomial, because it's a polynomial, you account for lower powers.
Okay.
So with that in mind, does this make sense? Now we're accounting for t squared, t, 1, t e to the 4t, and e to the 4t, right?
Mm-hmm.
And that's how you assess what you need to add there, by looking at your particular solutions.
Okay.
And then, so what's the next step? You just have to what? We did this before. Do you remember what we did?
So here you just set equivalencies to each other with the same.
Yeah, you remember.
So what would that be called? Like the e to the 4t, like the technical term, would that be like, what would you call those? Would you call those like the e to the 4t's on both sides?
Yeah.
How would you call that?
Like what is it, or what do you
where
call
you
it?
would set two things equal to each other.
Oh, okay, I see what you're saying. This whole thing, what we're doing, this method, this is just equating like terms.
Like terms. So the like term here is the e to the 4t.
Yeah, equating like terms. This is I mean that's a mathematical way. But then the one thing is, all you have to do when you're doing method of undetermined coefficients is, the reason why you're doing this, first of all, right? The reason why you're doing expanding the terms is because you have to solve for these undetermined coefficients. You have to solve for these undetermined coefficients.
Okay.
And then a mathematical construct would be anything on the right-hand side that has the same like term as anything on the left-hand side, you can make them equate each other, right? And that's just what it is. You make them, all the like terms on one side can be equated to the right, to the other side. And that's just an algorithm of solving for whatever's inside this while discounting the variable. Now you can just discount the variable, right? You can because they're in both sides, right? And then the only thing you have to solve for are the coefficients of those variables.
Mm-hmm. Okay, and why did you because I noticed that you were doing that to solve beta, why don't you need to account for that a1 being 0 as well?
Oh, I see what you're saying. I answered this question last time, I remember. It's because you don't want to discount. A1 cannot be 0. It cannot be 0 because it was in the particular solution. If you make it 0, you're pretty much saying, let's discount. What was the A1 term in the particular solution? This A1 term is the t squared terms, right? Right?
T squared.
Yeah, look at this guy. Look at the prompt, the problem prompt. The YP, the A1 is in front of the what? A1 is in front of the what? The t squared, right? If you make A1 0, you're discounting the t squared term. Sometimes they call this A1 can be 0, yeah? This whole thing, you can even say A1, A0, A, and this guy, right? You can say A1, A0, B0 are all 0. You can say that, right?
Okay, what's the issue of having t squared as 0?
T squared, let me see. We can't do that one because it's not, it cancels out, right? It cancels out right here. It cancels out right here. So that's why it's A1, B0 equals 0. These guys cancel out. So you don't even have t. You're just solving for the coefficients. Or you're equating the coefficients so you can solve for them.
Okay.
Yeah. So, I mean, the A1 again can't be 0 because you're discounting for the t squared terms. Another time, other times in math, they call that the trivial solution. If A1 was 0, then it's the trivial solution. And then you don't want the trivial solution because that's always a solution to your differential equation. Like, why don't we just make everything 0, right? But no one likes that one. So that's why you cannot make it 0 because you want a unique solution. You don't want a trivial solution. So because A1 cannot be 0, B naught has to be 0.
Okay.
Yeah, because A1 can't be 0. B naught, the only way that can be possible that like A1 times B times beta equals 0 is if beta was 0.
Mm-hmm.
Okay. And now, so we have beta. What do we solve next?
I guess alpha.
Okay. So we have so many different ways we can do that, right? But like, when we have like other equations, but the ones that work when we were doing this in Homer 5 is these two equations.
Okay.
And then this is just me simplifying these two equations. I wrote without the t terms, I just wrote them down right here.
Mm-hmm.
And then the beta is 0. So that term, this guy right here goes to 0. This guy goes to 0. And you're only left with these two, which are these guys. And then, this is just algebra. You just solve for alpha. It's -4.
Okay. I'll go through it and see, but that doesn't look too bad.
Perfect. Yeah. This one is actually, you're going to see this again. Just memorize the steps. Ask me again, but we could definitely go over it. But that's like the second time we went over it. So let's take a look at, let's see. Yeah, let's look at this one. I think this one is, the one thing I would like to do is actually go through like the step of solving for the full solution of the inhomogeneous equation, differential equation. So, okay, well, what's 3 asking us? Number
3.
Yeah.
It's problem 3.
Yeah. 3 has like 3 parts.
Okay, find a particular solution to the non-homogeneous differential equation. Okay, so
Okay, that's the first one. Okay.
second order, 2 derivatives. We would have to would we still use alpha and beta, that idea as well in here? Or
okay, so
is that a different way of solving this?
Okay,
solving
so
these.
the alpha beta thing, that's just on its own. Don't please, you would do the same thing, but don't remember it as that though, because like that way is just like that beta alpha thing. You're already given everything. It's just its own problem. But the way it's gonna make more sense the way we actually do the method of like undetermined coefficients is doing this problem. Once we do this problem, you're going to see what the process of why we're doing it. And okay, so what was always so you know how like in the alpha beta they already gave you the YP, right?
Mm-hmm.
For the most part, they'll never give you the YP. So the first step in solving or using the method of undetermined coefficient, the very first step is always look at your right hand side and give me the particular solution. So what do we have here?
10x plus e to the negative x.
Okay, so applying that table, what would you do? What's the very first so there's this guy right here. Oh shiz. There's this guy right here. So how do we apply that guy?
Okay, so you would have ax.
Okay.
And then plus b e to the negative x, or
so this is a polynomial, right? This is a polynomial.
Okay.
So when it's a polynomial, you account for what? What was that one thing that the rule?
So you account for all the lower order things. So you have a 10x, so but you don't have a constant. So you would do ax plus b?
Yeah. So yeah, you have ax plus b because this is to the first power, and then you have a 0 power, which is a constant. So it's ax plus b. So that's it. That's for the polynomial that accounts for that solution. So that's good.
Okay.
And then now you have the second thing, transcendental function, exponential. What is its particular solution?
Well, I guess from memory, it's c times e to the negative x, or by itself just a.
Yeah, but for the most part, when you're doing this, try to do like a sequential thing. Well, what is that?
Sorry, we have the ADT alarm system.
Oh,
I'm in the
shit.
same room as the thing. I don't
No,
know.
like
Sometimes I hear in the background that sounds like your security system or something.
I do have ADT as well.
Yeah, I guess because we have the pulse system, I'm guessing.
Oh, you guys have the pulse one? I have I think mine is a little current. I think I forget already.
Yeah,
That's good.
is it like center or something?
Something like that, yeah.
Okay.
Okay.
Let me see if I can try to turn. You guys, no way, I'm already showing. Okay. Can you still hear me, or am I a little quieter?
No, I can hear you. I can hear you.
Okay.
Okay. So does this make sense? Like, I think, well, yeah, what you told me is pretty much, hands-on, like, or on spot. Like, it's pretty much what it is. That's what you do.
Okay. Let me see if I can try to change the. I think I have the sensitivity up too much on my microphone, so I'll turn that down a bit.
Yeah, no, that was like super close. So it was like, it seemed like it was super close, but I don't know. It doesn't matter though. Try this one, like try inputting this one, like see like if you, what does it say?
X plus b, yeah. I think my parents let out the dogs, so it's probably going to be another loud sound coming up.
Does your ADT thing, does it tell you, does it speak, or does it just beep?
It just beeps. I think there was an option for that, but we decided not to use that.
Yeah, because mine's, it does like, yeah, it does do that. It speaks, and it's pretty, every time you open a door.
Oh my gosh, no, it says AX is not defined in this context. So is it
did you put times? Did you put like the times?
A times X? I can try doing that. I think it just says A is not defined. Let me see.
Why is it doing that? Like,
A variable A is not defined as context. So I guess maybe the latex form \math A.
Oh my goodness, you could figure that out. I don't want to put up with that. Yeah, go ahead.
Let me see if that works. I don't know, because
That's super weird.
no, it doesn't.
Okay. Anyways, just it doesn't really matter. I mean, like what matters is the exam, yeah.
Yeah, but the problem is it's going to be done through the system too. The exam.
It's gonna be done through a system as well.
Yeah.
Oh my goodness, are you kidding? That's not good.
Yeah, I don't know, because he says it's going to be pretty similar to the homework that you were working on.
That's good. That's good. That's actually good.
He gave her a review, so I think I can find it and I'll send it to you.
Okay, he gave a review. That's awesome. I was just gonna say, like, do all the homeworks again. You have like 6 homeworks, so just do them all. Speed is always the issue. So like, if you do them like maybe 3 times, then like you at least remember, muscle memory.
Because the brain's the muscle.
For math problems, that's always the case for me, because you have to like memorize them. It's like a math thing that you have to memorize. Like, it's not like physics.
But
what does it say?
That makes sense, what you're talking about. I just don't know why it's not accepting the form.
Does it have like a contact? Like, did it have like a contact info where you could like console?
Not that I think of. I know one of the calculus books, I think by Larson, they have a calc chat where they offer live help for the solution. So you put in the problem if it's an odd number, and you can talk with someone and they can walk you through it for free.
And then that thing, is it connected to the system?
Well, it's connected to the problems, yeah. So any problems that you have that are odd numbered, you can actually,
Okay.
I think it's even, because I think odd is like the standard for work problems. But
Yeah,
anyway,
usually. Okay,
it's
whatever.
kind of neat.
Just take care of that one. Like, but then yeah, that's you need to solve the issue, because then your whole exam is gonna be wrong. You know.
Yeah, it's gonna be done, I think, through D2L, which is like the
I would never do that. Like, why can't your professor just correct the assignment, the exams by himself, or the TA? What's going on?
yeah.
I mean,
This is a
why are they getting
differential.
paid?
They already have too much work to do. So anyway, so let's
Dude,
see. Okay, so the midterm is going to be on Friday, October 16th from 8 p.m. to 9:15 p.m.
October 16th.
Yeah,
Oh, that's good. Yeah,
October
yeah.
16th.
Yeah, okay, that's more than enough time. Good thing it wasn't on Monday. Okay, so like what I would say is like this isn't really that bad. This homework 6, as long as just follow the steps that I'm gonna talk about now, and then like on number 4 and 5, those are like the main things, and then the alpha beta ones, that's like the main thing.
Okay, so let's see syllabus, and then okay, practice problems 1.
Yeah.
Okay, so it does look like it's through web work too, because
Oh,
I'll download the file and send it to you now, and you can take a look at it, because I think you
okay.
get it pretty quickly. So we still got like 30 minutes.
Okay.
So,
Yeah,
so
we can probably
save.
cover those on Sunday. And then what I'm gonna try to see how many like whatever number of problems there are. I'm gonna see if I can solve those ones, like the ones that are difficult, or maybe like all of them.
Okay.
And then so that before the next week you could just like plow through all the homeworks and the review.
Okay.
How do you usually study for like these kind of exams, math exams? I guess it's different for
So
everyone. So
yeah, for me, I really don't know. Sometimes I look through just older problems. Sometimes I'll look through my notes and go through the examples and the notes. I really
okay,
don't have a consistent, like the same thing
way, yeah,
way, because I try to be dynamic in case
that's good.
to be
Okay,
fitting for every class. But I think usually it takes one exam for me to determine how I think I'll study, and
study.
then
Yep, that's usually
I'll
the
do the
case.
others.
Yeah.
But it's been difficult. So I think probably just work through the practice problems, maybe the homework
Yeah,
again.
I would say that's why we're obviously gonna have the solutions for the homework 6. Just do like homework 1 to 6, mainly like obviously the review, like practice problems. And then I don't think if it's gonna be similar to the homework, there's really no conceptual stuff, barely any conceptual stuff.
Yeah, you can, if you could take a look at, just you don't need to like answer any questions, but
Okay.
let's see. So I just sent the practice problems PDF file, and
Oh, okay. I'll look at it. It's not going through yet. Let me see.
it's no preview available. Download. Okay, yeah, here it is. So yeah, it
Okay.
might take a little while.
Can we go over this though? Because this is very important.
Yes, yes,
Okay, because yeah, this is like the main thing. The Chopin. Okay, so after you get this part though, right? You get the YP
yes,
part. Okay. So the next thing after you get the YP is to solve for the homogeneous or the complementary, or this guy.
okay.
That's the next thing.
Mm-hmm.
Because you have the YP. The next thing is the YH or YC.
Yeah.
You know how to do that already. So that's just the homework 4 or 3. And then after you do those 2 steps, YP, YC, then you do the YP derivatives. Does this sound familiar? You do the YP derivatives.
Yes.
And then after you do the YP derivatives, what do you think you're going to do? We didn't do this, so that's why I wanted to go over it. Is now you have to solve for these undetermined coefficients. You have to solve for them.
Mm-hmm.
And then how do you solve for them? You you do the method as we talked about. You put the YP where the Y is.
Okay.
You know, and you do that, and after you do that, you know, you're gonna get a bunch of terms that's like very complicated. And then like you put, you know, you look at the YP, and then you assess. I need to put like missing terms here, missing terms, and you do. You have to put missing terms. There's only a 10x here. There's only an x term. You have to put in the constant term. So the constant term is just 0, right? 0 times 1, right?
Yes.
Okay. So you have this 10x, you have this 0 times 1, and then you obviously have this other term. So you started with 2 terms, and now you have 3 terms. And then, you know, the right-hand side, that's what it is. And then the left-hand side, you have to do some simplifications, and not simplifications. You have to, like, you know, after you plug in the YP, you expand these guys. You just, you know, you times them by the coefficient that's already in the differential equation, and then you assess what things are equal and like. So equal and like terms, you assess, you make them equate each other, and then you solve. Obviously now you see this, right? There's three equations, right?
Mm-hmm.
And then how many undetermined coefficients do we have? There's 3 equations.
A and B, so you would have 2.
What about C?
Oh, so then you would have 3.
Yeah. So B was obviously, it could be 0. We don't know yet, but we want to carry it over. So we have 3 equations and 3 unknowns, right?
Mm-hmm.
3 equations, 3 unknowns. Sounds like it's legit. So that you can definitely solve. So you solve for C, solve for A, solve for B. And that's the thing. That's the undetermined coefficients, the C, A, B, and C. And then so when you have that, once you have that, right? Once you have that, you just plug it in back at the YP. The YP is the one that had the A, B, and C, right?
Okay, you have A, B, and C. So that vertical line down, is that treating A like further down where you drew the A, B, and C, the YPX.
Oh, I
and then
see what
the
you're
A,
saying.
B, and C, is that treating A, B, and C as constants?
This guy right here?
Yeah.
Yeah, A, B, and C are constants, which they are, right? These are constants.
Okay. So you're basically, you just look
Plug
at your
them in.
particular solution, and then you end up getting A, B, and C unchanged, or
A, B, and C are pretty much, you plug them in. You plug them in the number, the numerics. The A, B,
okay.
and C, now you determine them, right? Now you know what they are.
Yeah.
They're numbers now. So in the YP, what was our YP to begin with? Like we had this YP here, right? This is our YP in the beginning. We have this ax plus b plus c e to the minus x. You have this guy, right?
Yes.
So now we just plug in the a, b, and c because we know them now. We solve for them. So after you plug them in the YP, and then, you know, what was it? What is the total solution for the inhomogeneous equation? What do you do? How do you form the solution? You add the what? You add the complementary solution to the particular solution, right?
Uh-huh.
So you add the complementary solution to the particular solution. That's a concept.
Okay.
So after you do that, like you just plug them in. What was your YC? Your YC is this guy. I'm just gonna mark it a different color. Your YC was this guy. This is your YC. And then your, I guess it's yellow. Your YP. Your YP is this guy right here, right? That's your YP. And then, you know, plugging in just going back to a different color, plugging in the values here. for A, and this is B, and this is C, right? A, 1/2, B, minus 2/5, C, 1/2, right?
Mm-hmm.
And then you look at this. You still have C1, you still have C2, right?
Yeah, so.
And now I'm gonna explain this.
Yeah.
Let me ask you first. Does this one make sense?
I think so.
Okay, that's good. So now you see this. You've seen this before, right? What, C1 and C2. Is this a particular solution, or is this a general solution?
Mm.
What is this one? Is this a particular solution, or is this a general solution?
Well, knowing that you've already added the particular, it should be a general.
It should be general, but then this particular thing, it actually just means, yeah. When I say particular, when I say particular, this just means did you apply your initial conditions? Did we apply our initial conditions yet?
Initial conditions.
We don't even have them, right? We don't know what they are.
Mm-hmm.
So this is not a particular solution. This is just a general solution.
Okay.
And obviously, what did the initial conditions give us? Just concept wise, what did the initial condition give us?
Well, I don't know how, like, definition wise, but I know that you basically multiply the initial condition throughout the differential equation as you solve it.
No. Okay, let me just go back. So when you're given the initial condition, you can get the particular solution. Oh no, yeah, let me go back. The initial condition gives you the C1 and C2, right?
Yeah.
And then and so once you have C1 and C2, you plug them back in this guy, and it gives you a particular solution. So it's the same thing. It's the same thing. That's always the flow for like these differential equations. Like you're given a differential equation. You obviously find a different. There's different algorithms to find the general solution. And then like if you're not given the initial condition, you only have the general solution. If you are given the initial condition, you find the C1s, the constant coefficients, and then once you plug that in, you get a particular solution.
Okay. What exact, like, because I know that the initial condition form is like an integral, but
It's an integral.
Yeah. So is there any other form outside of that where it's just initial condition is?
It's a differential, right? Isn't it a differential?
Okay.
Like this guy.
So because I know, like, if you're like given initial conditions, how will it look?
How will it look? What do you mean?
Like in a problem, they may ask, given the initial condition, and then so and so, what will the initial condition look like? How will I be able to identify this is an initial condition?
Okay, good. Okay, so that right there. When try look at number 5. Try look at number 5.
5.
What does it give you? Or tell me what it gives you first.
Okay, it gives you y of 0 equals 0 and y prime of 0 is 0.
Yeah. What does that look like?
I guess then those are the initial conditions.
Yeah, and that's why it's an initial condition, because you know a data point at y. That's how you
Okay,
know it.
so since you said that it's a differential, would that mean just the y prime of 0 is 0?
Yes, at 0. Yeah, y prime of 0 is 0 at that
Okay.
point.
So if y prime of 0 is the initial condition here, what is the y of 0 equals 0?
That's another one. There's 2 of them. There's 2 initial
Two initial
conditions.
conditions. So it doesn't have to be a differential. It can just be things given.
Yeah, it doesn't have to be a differential. And then this is how you know how many you need, because someone could ask you, oh, here, someone could ask you, conceptually, I have one, derivative, right? This is a first order, right? This is a first order differential equation, right? right?
Yes.
Because you only have one prime. And my question to you is, how many initial conditions do you need to get a particular solution?
1.
And why?
Because you have y prime.
So the degree of your differential equation tells you, right, how many of these you need, right?
Yeah.
So these are concepts that people usually ask. Like, it's just those things that linger after the class. Like all these other algorithms, it doesn't really matter. You're gonna look back to it and it's like, oh, you know what? I don't even care if I knew how to do it. But once you take linear algebra, finite elements, all of those, right, you're gonna be like, someone's gonna ask you like, okay, how many initial conditions do you need for this differential equation? And it's always dependent on the degree of your differential equation. So 1 degree, first order, you always need only one. You only need one. And then if it's a second order, you need 2.
Okay.
1 and IC 2. And then so when someone gives you the differential equation and he gives you also the initial conditions, this is a well-posed answer. They always say this is because you can. This is called an IVP, right, or a boundary value problem, right?
Yeah.
And like when you're right now, you guys are working with like ordinary differential equations, right? ODEs. You guys are doing ODEs, right?
Yes.
But eventually, you're gonna do partial differential equations. And partial differential, like right now, you only have these like these differential terms in terms of one variable, right? It's either like t or x, isn't it?
Yeah.
But eventually, once you get to partial differential, they're going to be 2 bivariate variables. You're going to have an x term, and you're going to have a time term. You have this time term, which there's some physical structure now. It's not just like math. And this x term is usually position or space time. So space time is in partial differential, but ODEs you have this yx yt. Anyways, like that's just to like relate all the what it could be.
Okay. If you have 2 initial values, like if you have a second, like there should be, like if you're given 2 initial conditions, and let's say like for that second one that you wrote, which was a y double prime plus y prime plus y, and they give you the y prime of 0 as 0, for example, and y of 0 is 0. Since you're given y prime of 0 is 0 as one of your initial conditions, could you substitute in that for the y prime in the problem? So
this
like,
guy in the problem?
yeah, could you relate those 2 together?
Not directly. Not directly.
Okay.
It's not how you would do it. It's you have to go through the process. You have to get a general equation first, and then general equation plus the initial conditions gives you the particular solution, a particular equation.
Okay, so you don't need to like set up a additional thing to account for the y prime. You can just do just one for the y double prime and have 2 initial conditions and solve from there. You don't need to, since you have 2, I guess you're given a double prime and a single prime, you don't need to use 2 initial conditions to account for just a double prime, and then you don't need to make a 3rd initial condition for the y prime by itself.
Okay, let me try to unpack that one. So if you notice, like if you take a look at this like so many times and you have so much time in the world, if you have like a first order, let me just write out down here. If you have like a first order, right?
Okay.
If you have a first order differential equation, all your initial condition has to be a 0th order.
Right.
It has to be 1 order below your maximum degree of your differential equation. So if it can't be the same degree. It cannot, because you don't know that. You don't know that point. You only know because it's a differential. It's not defined. But what is defined is the one after it, the degree below it. If you have a second order, then all your initial conditions, you can only define it in the first order and in the 0th order.
Mm-hmm.
So
okay.
you don't have to like that's it. Like you're only defining the 1 for the first order is
Mm-hmm.
just for this guy, and then the 1 for the 2 for the 2nd order is 1 for the y prime and 1 for the y.
Okay.
That's usually the case.
If you have, let's say, a 0th order differential equation, could you find a particular, an initial condition for that?
Hold up. Let's see. So say that question again.
So if, let's say, you just have a 0th order differential equation,
okay,
would it be possible to find an initial condition for that?
Oh, okay. I don't think you even need it because it's you could already solve it, right? It's just algebra.
Oh, yeah.
Yeah, I mean that is the initial condition. Just solve it.
Yeah. So that's a part. So you wouldn't need to find complementary or particular for it.
Yeah. The only reason why, for the most part, there isn't that, there's the first order, 2nd order, and then like multivariate orders or multi-orders. But there's, the 0th order is usually just solved for it. Okay. Let me just go over before we go. Let me just go over this number 5. Number 5 is a little probably the most difficult problem.
Okay.
And then I'll send you if you saw my email, I didn't really give you the solution for 8 to 11, but they're all pretty much the same. It's gonna be the same as number 5 right here. Okay, can you give me 1 minute though?
Yeah.
Okay, hold up. I'll be back.
Mm-hmm.
All right, I'm back. All right. So I guess we'll cover this really fast. So did you look at number 5?
5 is you're given 2 initial conditions.
Yeah. Oh yeah, this is the one that we had to look at. Okay, but then what is it asking us? This one is a little weird. It's hopefully
the maximum value.
So this one is like a step further. Like if you just imagine, conceptually think about how you're gonna do it, thought process. Like it's not asking you for the solution, right?
Mm-hmm.
It's asking you for the maximum value of the solution. So what does that mean?
So you're saying if x goes to infinity or something,
yeah,
what would y be?
Yeah. Do you remember the maxima minima in calculus 1?
Like relative max, relative min? Or no, that's graphing.
When you're trying to find optimization problems, when you're trying to find the maximum of a function, what does that mean?
So maximum.
I want to maximize f of x. What did you have to do?
So it's kind of like an inverse relationship where when x is going to 0.
But what did you have
limits?
Yeah. Yep. Yeah. What did you have to find though? How did you find the maximum value of that?
Value.
You had to find the derivative somehow, right? Right? You have to find the derivative, right?
I would assume because everything in calculus 1 is involving derivatives and limits.
Yeah, I know. But when you're finding a maximum value, you're usually finding the zero, when the first derivative is zero, right? That's the maximum value, or that's the x of your maximum value. When it's asking the maximum value of y, the very first thing is you need to take the first derivative and make that equal to zero, so you can find the x where that y is maximum, right? I think this is something you guys done many times probably.
Yeah, I mean, I remember optimization, but I don't remember this kind of process.
Okay, well, this is what you have to do. When you're maximizing the y, the very first thing is you find the y, obviously, the y equation. What is the y function? And then you take its first derivative, and then you make it equal to zero and solve for x, where that is equal to zero. And then the next thing is, now you've solved for x where the y prime equals zero. Then you plug that in. You plug that in the y equation. You plug it in the y equation. The x where the y prime equals zero, you plug in the y.
Okay.
And you get the y max. You plug in this x that you solved for in the y equation. Then you get the y max.
Okay.
Yeah, so this is another one. Besides, like, the pool of problems that you can see in the exam, maybe like an alpha, beta. And then, the IVP, BVP. And this is for like second
what
order.
what was BVP?
Boundary value. So the IVP is initial value, right?
Right.
And then, like, this is just another name. Maybe just throw it out the vocabulary list for now.
So initial value. So are there any other names for like boundary value problem, like extreme value, or?
No, like I'll just define it since we talked about it. The IVP, the initial value problem, this is when in the variable, the dependent term, or the independent term, the independent term parameter is t. And then the BVP, boundary value, this is when it's space. This is when it's space.
Okay.
So time and space, two different names, same thing. So, initial condition is given for the IVP, and then boundary condition is given for the boundary value. But they're all pretty much the same. The only difference is you're using T for the IVP, X for the BVP. Okay, anyways, so the pool of problems can be like the alpha, beta, the IVP, or BVP. And then the other one can be this guy, whatever we're solving right now, this Y max. He can definitely ask you this question. Okay, just to breeze through it. So did you understand like that concept where you find Y max by doing this, by like taking the first derivative, making that equals to zero, get the X, plugging in back the Y?
I mean, for real basic derivatives, yeah, but no, not for these.
But that concept right there is, you can apply it. You'll see it, because then in the end, you're gonna get a Y of X. You're gonna get an F of X, and simply in like calculus 1 or 2, whatever, when it asks you for maximum value, they already give you the function. In this case, they don't give you the function to do that. They want you to find the function, which is the solution of your IVP. Okay. So you do the same steps. I kind of didn't do the 1, 2, 3 step by step 1, step 2. But what was the first step? The first step, the first and second step are kind of interchangeable, but the one thing you want to do is either find the complementary, right?
Okay, and then one complementary.
And then the next thing is find the particular.
Okay.
This can be interchangeable. You can do this one first. You can do this one first. It doesn't matter. And you're going to combine them in the third step. So you do that. After you do that, I'm just going to talk about high levels. We can cover this on Sunday. All right, I'll send this to you. So with that, what was the next step? In the YP, you put that back in the differential equation, right? You put the YP derivatives back in the differential equation. And then you solve for the undetermined coefficients, which is D and C in this case, right? And then, so I use D and C for the undetermined coefficients. Then I use A and B instead of C1. This is pretty much C1 and C2 for the complementary solutions. So this is a way like that you could do this. You don't have to use C1 and C2. Then you can continue your coefficients for the particular solution. So after you do that, the next thing is you combine your complementary solution and you add a linear mapping of that to the particular solution.
Okay.
And then so the particular solution here is this guy, right? And then the complementary solution is this guy. You still have this A's and B's, right? After you did the undetermined coefficients, C's and D's, they're gone. They're already in here. So now this is the general solution. This is where we left off. This is the general solution. And in order to get a unique or a particular solution or unique solution, you need to apply the initial conditions or the boundary conditions. Yeah. So our boundary conditions or initial conditions are given to us. We just have to use them. So the first initial condition is y0 equals 0, right? And then so we just use that in this equation right here. And we get that b equals 0. And then the second one, y prime of 0 equals 0. So this one is for the first derivative of the general equation. And then we plug that in, we get a. So we have b and we have a. So b is 0 though, so that's good. We only have two terms. So we have our particular solution, and then we have our complementary solution with you solve for the a. So now you plug them in. So this right here is your unique or particular solution, whatever, And so this is your f of this is your y of x, right? This is your y of x, right?
I guess so.
Yeah, after you do all the steps, so this is y of x. But then now this is not asking for that. It's asking for the y max. Where is your function y maximum? So the steps are you have to find its first derivative. Taking so many derivatives, like pretty much it's crazy. But now the first derivative will tell us if something is maximum. And how you do that is you set the first derivative equals 0. And you find the x. You find the x in your first derivative when it equals 0. And this is not hard, but you have to go back to your trig. So you just find whenever it equals 0. And these are the candidate x's. And do you remember like how you find like whether they're maximum?
No.
So how you find when they're maximum is after you find the x when y prime of x equals 0, you plug in the x's to y of x. Like these x's, each individual x, you plug this back in the y of x. This problem is really long. This problem is like probably gonna be the one that's gonna take you the longest. But so you plug them back in the y of x, which is what we have here, the y of x, and then you look at what the number is. After you plug them in, you look at what the number is. The y max is obviously the largest one, right? So let's take a look at that. So I plug in x equals 0 in y of x. This is the one. And I get y of where x equals 0, I get y equals 0. And then so that's this guy. Now I plug in 2/3 pi. So I plug in 2/3 pi for x. What I get for that is this guy. So x equals 2/3 pi. 2 pi over 3, 2/3 pi. It is 2/3 pi. 2/3 pi. And I get negative root 3 over 2. So I get a 0 for x equals 0. I get a negative root 3 over 2 for 2 pi, 2/3 pi. And then you can obviously do the math for this other one, for this other guy. The negative 2/3 pi and then you get a positive number. You get a √3/2. So now let's take a look at that. Let's take a look at those numbers. So you have a y equals 0 equals 0. You have a y 2π/3 equals -3 √3/2. And then you have a y 2/3 pi equals √3/2. Which one's maximum? Which one's the largest number?
I guess the positive one.
Yeah, it's this guy.
√3/2.
Yeah, it's this guy, right? This guy is like obviously low. This guy's a negative. It's the lowest one.
Oh, I thought we were comparing negative √3/2 versus positive √3/2.
Yeah, I mean we're comparing three of these guys. We're comparing three of them.
Three.
Yeah, there's x equals 0, and then x equals 2. There's three ways x can be. We found three x's. We found three x's. You just have to go to the math. There's three solutions to the x, and then you plug them back into the y, and then you just find where y is max, which is like the largest number. And then so that's the answer. Wherever the y is like the largest, that's the answer. It's this guy. Yeah. What do you think of that one?
No idea what to do on it.
Yeah, look, we'll cover this again on Sunday. Definitely, this one's like one of the longest ones. This is like probably the peak of like the first exam is solving this y max. Okay, so I'll take a look at. I did get the review. I'll look at that and then like try to like see if you can do some of those like before Sunday, and then we'll kind of discuss it.
Okay.
Cool. All right, man. Yeah, thank you so much. And then yeah, I'm hoping that did this table at least make sense? Did this table at least make sense?
The table made sense. Yeah. I'm just I have almost no confidence on this exam coming up.
You have to like, the thing is, do you have time to practice the problems, the homeworks? That's the thing. Do you have time to practice it? It's gonna get easier the more you do the problems.
Yeah.
Can you at least do the problems though? The like again like homework 1 to 6, and then like the review, practice problems.
Yeah, it's just the past couple, I guess, homeworks did, I guess, makes like at least the past two. Okay. At least had some sense, but the previous, I guess, 3 others, I don't know.
Okay, which ones are those? Which ones are those? Is that
homeworks 1 through 3.
Okay, I'll try my best to. I'll try my best because it's a lot to actually like work those out, like the solutions. And if I were to focus on something, should I just like maybe look at the review? Is he gonna give you guys the solutions to the review or not? By the way,
I don't know about that.
Okay, so like should I? Okay, because I was thinking about like because I still have to do the T10. Oh yeah, T10 is due next week. Yeah, you said.
Yeah, T10, T10A. They're pretty short each one, but.
Okay, so should I just focus on doing the differential equation class for Sunday? I think so.
Yeah, I think that would be good. I guess just the practice problems, go through those first, and then.
Practice problems, okay.
Yeah, and then after that, I'll look through the other homeworks. So I think it's built into it.
I think
based off of the others.
I think that's better. Yeah. Let me give the solutions to the practice problems. I think it's not bad. How many problems are these?
Okay, there is
23. Holy crap.
Okay. Oh man.
It's a lot of problems.
Yeah, and I'm trying to fill out this transfer application that's due on the 15th.
Oh yeah.
And I have exams all of next week too, so
Can you move that one, the 15th deadline?
No, that's the school's deadline for the
Oh,
transfer application to apply Texas, which
I
is
see.
the not the scholarship, but the application itself. So
Oh man. Okay. Yes, do your best. What I can say is, so I'll focus on the review for the differential equations. I'll give you the solutions up to a certain point. Like if I can do all 23 in like 2 days. Uh, so I'll do that. But then obviously, like we can still talk about it. It's not the exam's still not until Friday.
yeah,
So we'll talk about that, and then I'm not gonna do the T10 yet until like next week.
okay. Yeah, I don't think I need too much help on those two sections, especially because I think T10A is one page, not a sheet. It's just one single page. So
Oh wow.
T10A won't be an issue. And then T10, I don't think is too long either.
Yeah, I think we should focus our mind in like I think you got those more than the math, right? Like we should focus more on the math.
Yeah, I guess just at least get one with more experience. But even physical chemistry, I almost am clueless on that too. So
But the exam isn't till is it next week? You said we'll
yeah,
do our best.
it's on Wednesday.
Oh, it's on Wednesday. It's before the math.
Yeah, before the math.
Okay, how do you want to study for? How do you want to study for that one?
Oh boy.
Is it possible for you to like tell your professor to move one to the other week?
Well, he said if that's not possible that day of the week, you can move it to a different day of the week with an
That's
oral exam.
an oral exam.
Yeah, where he gives you the problems and you have to speak how you do it, like
Oh,
how
I
you
would.
solve
I think
with.
I'd rather have that one. Yeah, you should. Why don't you do that one?
Because see, I don't. He didn't really explain very well what he wants in an oral exam
I
either.
think that's. I think that's good because then you don't actually have to solve and study for it. You just have to know conceptually.
Yeah, I'm gonna probably ask him a little more detail on exactly
Yeah,
what's for the
try,
oral.
yeah, try like maybe do this like because like what would be nice. I always do this is if you can move one of those exams to like a different week, then you can focus that whole week for one of your classes, right?
Hmm.
Try see if you can do that just for your case, because so that I would really like you to get an A in like both these classes.
Yeah.
So like, try. Let me know what happens when you ask them. But in terms of the math, I don't think it's any issue as long. I want you to actually do the problem though. Can you do the problem like one by one?
Yeah, I pretty much did that on the previous homework.
Okay. Yeah, just do homework 6 like one by one. I did give you how to do those,
Hmm.
and then we'll look at those again on on Sunday, and then like if you have any questions, and then cover like maybe homeworks 1 to 3, similar problems. Obviously, they're gonna show up on the review, right? Those problems are gonna show up on the review. So we'll cover the review on Sunday, and if we need to, we can do more problems like from homeworks 1 to 3. Okay,
Okay.
does that sound good? I think as long as you do the problems, like dedicate time to actually do the problems,
Hmm.
no matter how much it takes. At least understand, like you can carry out the steps that I'm doing. If something doesn't make sense, let me know so that like I can explain what steps. But as long
Okay.
as you do the problems the same way, because you have to find a systematic way of doing it. You can't just do the problem and like figure it out.
Yeah.
You have to do it very systematically, and that's the only way you can like really easily figure them out if you do it like in a systematic way.
Yeah.
Okay, all right, man. Have a good one.
Yeah, you too.
See you on Sunday.